Thank you, Andres, and thanks everyone for attending. So I've been working on that for about a year, so linear types for GHC. I'll explain what it means. But I'd like to start with something about garbage collection. If that works, it doesn't. Of course it doesn't. Oh, no it does. Good. So suppose you have two computers, two different computers, and they're doing exactly the same thing, but one of them you've implemented with malloc and the other one you've implemented with a garbage collected language. Complexity of the code notwithstanding, they tend to work about the same. When you have the garbage collected implementation will have, most of the time, when they do allocations, most of those sort of subparts of your code will be faster because they take advantage of pre-allocated memory. But once in a while, in blue here, you've got a massively longer allocation because the garbage collector is firing. We call that a garbage collector's pause. And pauses are not really a problem because they're amortized over time because the other allocations are much faster. So at the end of the day, the malloc and the GC implementation, they will take about the same time. But now imagine that you have more than one computer and you want to distribute the same task, and you still have your two implementations. And, well, it's not the same anymore. You don't, because it's quite obvious, the GC implementation is much slower to perform the same task because the pause becomes a bottleneck. Everyone is waiting on it. So despite the fact that most of these subtasks are smaller because fewer allocations, etc., the machine that happens to be firing GC at the moment will just slow everyone down and will just wait for it. And as can be seen, that most of the machines are completely idle most of the time in the GC implementation, whereas the malloc implementation has much more consistent time and will have much better usage of your hardware. And basically, if you have 4 machines, it's not much of a problem, but if you have like 1,000 machines and you're distributed something massive like your Facebook or Google or something like that, well, that actually fires all the time. And there's this Spark tool, a framework for doing MapReduce-like computations or pipelines like that. So it's a distributed programming framework, and they have documented running in this issue. We'll come back to that a bit. But so before I kind of speak about how we want to be able to address that, I want to explain a bit how garbage collectors work. So what's garbage collection? At the end of the day, you allocate data. Some of it is useful. We say it's live, and some of it is useless because no one is going to speak about it anymore. We say it's dead. And the role of the garbage collector is to remove the dead bits so that you don't use too much memory. At the extreme of the scale, there are 2 strategies. You could say, okay, never mind, I'm never going to reclaim any memory because functionally it's the same. It's very fast, but it has a bit of an issue in that you're going to run out of memory fast. I mean, like in minutes, probably less. So it's not much of an option. Your computer will crash and your program will never terminate. It's silly. At the other end of the spectrum, you can say, I'm going to constantly monitor if there are any dead data, and I'm going to reclaim them and allocate them, et cetera, et cetera. That works too, but that's supremely slow. You're going to swamp your program with your garbage collector process. You have to be somewhere in the middle. Where exactly? Well, there's no real one-size-fits-all solution. So GC is full of trade-offs. And one of the important thing, one of the heuristics, that tends to be done is called the generational hypothesis. And it says the load I'm going to receive has structure. And the structure is when I allocate something, it's very likely to die soon. But if something is a bit old, it's more likely to live for a while. So the way, one way really, because there are many, where garbage collectors do exploit that particular structure is, for instance, to split the heap in two, and we're going to call them the young heap and the old heap. And we allocate in the young heap, and data dies pretty quickly. And so when it's filled, we need to collect the data so that we're able to allocate again. And we do that by simply copying the few data that is left into the old heap, and that is super cheap. So that's not the problem. The problem is that when the old heap gets filled and you need to do garbage collection there, well, that's usually costly because data is older, so it lives longer, so there's more data, et cetera, et cetera. It's also usually bigger. So that's the general idea. But now, suppose I've got a piece of data that I come up with, and I do know it is long-lived. It's going to be there for a while, so it's going to contribute to many old collections. And old collections are what cause pause. So they're going to contribute to many pauses, and they will make my program overall slower because of the distribution effects that I showed earlier. So what do I do with that? So the GC is not particularly well suited for that, so maybe I'm going to manually manage that. I'm going to malloc my data, and when I'm done with it, I'm going to free the data. I mean, you can do that, and people actually do that, but it's just, I mean, we're Haskell programmers, right? It's not what we do, it's what C programmers do, and yeah. No, there's so many things can go wrong. You can use something after you free it, or you can access uninitialized data, or you can just forget to free something. And then we want it to be memory efficient, and we forget to, oh, no. But at the same time, I don't know about you, but I'm kind of jealous of C programmers. They can do all that stuff. I'd like to be able to. I mean, it's so much more precise. You can free memory exactly when you want. You don't have to rely on a GC. You don't have. You may control the pauses much better. So, moving on to my solution. This lollipop-shaped arrow is often called red lolly. Is a type constructor, and what I've been working at for the past few months is basically adding this type constructor to GHC Haskell. It's akin to the function arrow. It's a type of function. So what does it mean for a function to have this lollipop type? We say that a function is linear. Basically means that it uses its argument just the once, exactly once. So here, sucks uses its argument, the y, just once, so it's linear enough. But repeat uses it twice, we can see that. And constFalse, more interestingly, uses it 0 times, and that's not allowed either. So neither of the repeat or constFalse function below are linear. But I want to stress this is not a syntactic property of the text of the function. It has a deeper meaning. So let me go through this a bit more carefully. First, using is not really the right word. We use the word consume because it can be made a bit more precise. So here, f is linear because both in B and I, because the I argument, well, it appears twice, but it's in 2 branches of everything else. And I'm going to actually use one in my program when I call f, not the both of them. So I'm going to consume y really once. On the other hand, g at the bottom has a single occurrence of n. But it's passed to a nonlinear function, the repeat function from earlier. So that, since repeat will consume n more than once, then certainly g too. Because again, that is not a property of the text, that's more a property of the execution of the function. And h, interestingly enough, is not linear, because on one of the branches, you never consume I. Well, it's linear in B, though, but it's not linear in I, because in one of the branches you don't consume I, so it is possible in some executions that you will not consume I, and so it's nonlinear. And just to make things slightly more precise, the K function on top left over there, it is linear despite not really doing anything with I. It just passes it to the next function, passes it to the caller. So the real definition of a linear function that we use, I should say who we is, actually. So yeah, we've written a paper, and that would be with Simon Peyton-Jones, who talked earlier, and Mathieu over there, Busflug, you can raise your hand if you wish, and Jean-Philippe Bernardi and Ryan Newton, who are on there. So the definition for linear function would be when the return value is consumed exactly once, then the argument is also consumed exactly once. So that's where we start. But how does it address our problem? Because it does. Well, let's take things one step at a time. Imagine we have a sort of weird I/O thing, like the I/O monad, except the bind was not really, it's a bit different. It has lollipop arrows instead of regular arrows. So all the functions there are linear. Ha. So what does it mean? Well, when I produce a value or data in IO1 of A, then the only way I can use it is with a linear function. So a function that we consume the A exactly once. Ah. So if I malloc in IO1, then I get a pointer. And this pointer, I must consume it exactly once. So what does consume mean for a pointer? Well, we're kind of free to define it, well, but not intended. But so basically, the only thing that we are going to give in the API for malloc that does finally consume or eventually consume, oh, there's an IO1 missing. Free should be in IO. Sorry. That should eventually consume the pointer is free. So we are going to free the pointer exactly once, and that was pretty much what we wanted, right? So now, when we run the program, the do something bit needs to return a new pointer value that is a proof that it hasn't freed X. So we know it still exists. We still need to free it. And frees X, so it's called X prime here. And in do more, we don't have any more pointer to the reference, so we can't. And it will be coded by the type system. It becomes safe to do malloc. Actually, we can do a bit more, because why is malloc in IO to begin with? Well, kind of because of free. Also because we want to interact with the FFI, but let's forget about that. We don't want to use it with the FFI in our case. But free was a problem, because you free something, it changes state, so you can't really do that purely, right? Except we can't see X anymore after free. So we can't really observe that effect. So we might as well make malloc pure altogether. To be able to do that, we need to ensure that the pointer created by malloc is consumed exactly once. So we give to malloc a linear function that will be the consumer. Okay, so the type here is not super interesting because it always returns unit. There's a possibility to return something interesting, but that's beyond the scope of today. So here we just do malloc for the fun of it, yeah? just to heat the room. But humor me. So now we have the same code as earlier, and this code is entirely pure. Cool. So no I/O, it feels nice. You should get used to it, because it's one of the hallmarks of linear types. It makes more things pure. Because there are some effects that we hide and we cannot observe anymore. It behaves, it's referentially transparent, as we like in Haskell. I thought there's a bit of a problem that because of the question? Yeah? I'll repeat the question.
I'm disturbed by the type notator with the 1.
Oh yeah, sorry. That just means it's a linear binding for a function. So the question is, what is these double colon 1 over there? And I should have said that. So thanks. It is just a notation to say this is building a linear function. So it's because I didn't want to write the type as a type annotation. But it's just a reminder because the type system can catch that. Okay, this is just let's just assume that notation for today. It's not actually in the compiler anyway. Sure. So yeah, so I was saying there's a bit of an issue here. We can't deal with uninitialized memory, so we have to give an init value there because we have to fill the pointer right away. And it's probably going to be copied using the storyable. It's not perfect, but it's all short-lived value usually, so it's going to be not much of a problem for our GC pos since we were focusing on the long-lived values, right? Because the old collection is the problem. Well, but we'll come back to that because we can do better. So let's reflect a bit. I was just speaking about that, but yeah. So basically, our problem is old pauses. So we are kind of interested in reducing the time spent in these pauses by just taking things out of the old heap. And to do that, we took care of long-lived memory, long-lived data. We say, okay, these ones maybe I'm going to handle them myself. It's going to be a bit of a pain, but it's worth it because my application will run in reasonable time. And so linear type is kind of my answer to the question, how do we make that safe? Okay. But maybe that's not all, because I mean, data get, young data also get to the old heap when they live, and they can stay there for a bit and die, but that would trigger an old collection too early, and you will have, and you have many old data that is still live, and young data can be a problem too. So you do want to reduce the amount of young data, of short-lived data that you allocate in order to give more time for data to die, but for the next young collection, to make the young collection trivial so that they don't get old, and the old collection also triggers much later and with more dead data. It's probably important too. And well, I know it's important because I already wrote in my life a program that just killed the young heap bytes. The collection was like just a bit too early, and basically the young collection became long. That was horrible. Anyway, so GAC has a solution to that problem called fusion. We've heard of it in Simon's talk. It works with rewrite rules that the compiler can apply. So in DHC's standard library, you have specialized rules like this map thing that you do on lists. So you want to do 2 maps, but instead of allocating the intermediate list, you just say, maybe I'm going to do 1 pass, and this 1 pass, I'm just going to apply the 2 function. That spares you quite a bunch of data that would have been there just for an instant and been immediately dead. More generic rules, like the folder build rule, which goes into the stream fusion thing. And for instance, the vector library pretty much only uses stream fusion using the skip trick that Simon talked about earlier. But why do we do fusion? And we do fusion because we never ask the question, whose responsibility it is, or is it in that case, to allocate data? Because we know we're functional programmers, we're writing a mathematical function. So a mathematical function is basically the data is allocated by the producer of the data. That makes perfect sense. But this, then we have to count on Fusion to just remove this data when we write pipelines. But Fusion is not perfect. There's plenty of things that can go wrong. Maybe you're doing replicate here. So that's a function from the vector library, just makes a vector with only A's in it, and the same A. and you're doing replicate, and ultimately it goes to a file. So what you would do in C is you would memory map the file and you would write inside the file directly. But here you can't do that, so you will allocate a vector, and then you will copy the vector into the file. And you can't really fuse that. Similarly, in general, if you use a foreign function, it's not usually fusible because it's just is a function from like vector to vector that you've implemented in C. What can you do? Another variant is like you're writing to another computer. There's this thing in distributed computing called RDMA. It's quite popular nowadays, where you just write directly from your network card to another computer's RAM. It's a bit crazy. But you can do that. But if you start doing that, and you're starting to say, am I going to fuse my program across machines? Nah, that doesn't work. So of course, you will have an allocation there. This small thing is, when you do an unstream in the vector library, so unstream is the function that takes a stream and turns it into a vector again. And you, of course, you don't know the size of the vector, so you allocate a growable vector. So maybe you're going to allocate something of size 42, and well, you had a couple of hundreds of things to put, so you're going to make a 100-sized array to copy inside, et cetera, et cetera. That's a few unnecessary allocations and copies, but maybe you already knew because you were actually doing something that was like a map, and you actually know the size of the resulting array. And even if you're doing filter, you can overshoot the array and just be fairly safe. And it's a bit less precise in memory, but you can do that. But you really can't if you're only doing local things. And finally, and most importantly probably, inlining is super important, right? It's essential. You're using a function that consumes a vector, and it needs to inline to expose the stream interface. But that's a completely heuristic decision. GAC cannot know that, so it will just try and guess when it inlines something. And sometimes it doesn't, and your program suddenly allocates a lot. You can go from a program that runs in constant memory to a program that runs like in quadratic memory. It can really be absurd. It happens. It really does. So, yeah, it can be bad. So, more C jealousy. Destination passing style is an idiom in C, or Fortran, because, it was there too. Yeah, I'm going to tell you to program in Fortran. Yeah, absolutely. And the idea is, instead of returning a result that you allocated, you just take the space where you're going to write your data as a producer, and instead of being the producer that allocates the data, it is the caller. Of course, you're going to wrap it around so that you can recover the other one. OK, so that is not a real type in Haskell. We need to have some mutation. OK, ST or IO. Well, ST is nice because we can recover the other thing with run ST, right? We can turn the thing over and make a pure function because run ST does that. But I said memory map earlier. So IO? Well, OK, there's a solution to having both of them. That's called monoprim. It's in base. It is a tat verbose. So this is how we would do. So replicate would have that type, and mmap would only work in IO. But unsafe freeze, I'm going to speak about unsafe freeze, but it works in both. Yeah, so that's completely, it is correct. It's just super annoying. Otherwise you would be using it, right? So if you're not using it, why aren't you using it? Well, I'm not. I certainly don't. And there are so many problems with that. First, it's just annoying not to be able to write pure code just because we want to do something slightly faster. But also, things can go wrong. Unsafe freeze is really unsafe. You can make it safe by doing a vector copy, but we're trying to avoid doing vector copies. So that's kind of the problem. And it really is unsafe. So of course, if you're writing a small library function that basically takes an array, does some modification, writes it back into an array, unsafe freeze. And you can use that in ST and make that and expose a pure API. Well, that's obviously safe. It's trivial to use. But now, suppose you don't really know where the M vector comes from. Maybe it's a buffer in some other computer's memory. You don't know. So how do you know you can actually freeze? It's really hard. So you don't actually write composable big programs with unsafe freeze. It's just very localized. So it's not really a good programmation paradigm. So of course, I'm going to tell you to use linear types. So I changed the M into D just to mean destination, because they're a bit different from the M vectors. And we don't have ST or IO anymore, because again, linear types do make things pure. So here, consuming a D vector will mean filling all of its cells. So for instance, we give ourselves these two things. So we have replicate, that is the same replicate as before, and we don't really have to know the size of the array here. We just fill it entirely once. And it's not there anymore. You can't do that a second time. You can't forget to do that, because we only allocate arrays either with IO1 or with the same, by taking a consumer function. And that time it returns something. So that's much better than malloc, right? Oh, and by the way, we don't need the init thing anymore. So that's good too. So we could apply that to malloc. We won't do that today, but that's the same idea. And so split just takes the array and takes 2 bits, cuts it in the middle, and someone is responsible for filling one side, and someone else is responsible for filling the other side. And so filling both sides exactly once will fill the initial vector exactly once. So that fits a linear function to work here. It's a good type. And because we arranged it so that vectors are always consumed by a linear function, then we know that we will actually fill it exactly once. And it works with I/O, because pure functions work in I/O, and it will work in pure code with a lock. Yeah. So we're approaching the end, so let's have a bit of fun. I don't know if you noticed, but split is a bit like mappend, except like reversed. If I'm pointing that out, it's because it's not entirely a coincidence. And we can have quite a bit of fun with that, actually. So let's do that. And let's imagine we want to do continuation passing, not arrays, but no, destination passing, sorry, not arrays, but trees or lists. So I've got these D type here. Let's say we have a generic notion of destination, and we don't really know what it is, because I certainly don't. But it may not be the right way to make a type family like that. I don't know. Future will tell. But so, like a destination passing list, a destination for a list is just a slot in memory that can accept a list. A list is a pointer usually, so it's just a hole for a pointer. And same for trees, except it accepts the trees. And so basically, okay, I wrote the constructors a bit funny, just to highlight what happens. But when we add the D, we just like turn the thing around. So to build a tree, we take two trees and we make a new tree. And when you have a place for a tree, what we can do is say, okay, this tree is made up of 2 trees, and here are the places to fill in these 2 trees. That's destination passing style. And so now functions, they will take a destination to a tree and fill it in using node and lead. Yeah, sure, lead. Why not? Not D and leave D. And similarly for lists, and you can take, so you have a space for a list, you can say, oh, I just want to fill it with the empty list. And you have, or you can say, oh, I've got an element, so I'm going to say it's a cons, put the element there, and give you back the new destination where you can do things like that. So is it useful? Sure, at least in theory. So here's something we can do with that. So I've added an alloc function for destinations of lists. Okay, we need that at some point, and a generate function to fill in destinations when we don't know what things are. Using box representation is probably very easy to do because they're all the same, right? And below that, I wrote map in tail recursive style. That's kind of cool. Map is not something that you write tail recursively in one pass. Except in C, of course, because they always do that. They say, I'm going to just have a dangling point, a non-initialized pointer there, and I'm going to fill it, and blah, blah, blah. And that's the way they do it, right? If they ever write a map-like thing at all. But iterations on lists in C aren't like that. But here, we'll just do that in completely pure code, because linear types just hide away all the nitty-gritty mutation. Yeah, so maybe there's someone in the audience that want to be the person who says, but I've heard of this really cool trick called tell recursion modular constructors, and it does map in. Does someone want to be that guy? No? Okay. Well, it's fine. Because it's not a very good response. Because the thing is, there's things you can't do with that, like this. And yes, I've just written map with a full del, a single one. I think that's pretty cool. It highlights the fact that when you give yourself a good abstraction, it composes. And yeah, so you can do this sort of thing. It's just, and if you like the folder library, you can turn the folder library into making maps for you just by passing it a destination or something like that. Yeah. Yeah, it's for strict lists. Yeah, absolutely. Because there's no real point in doing this sort of thing. You can't access the list until it's done, right? So it is for strict lists. And that ties in very well with my next slide. Because maybe I've been lying to you. Maybe this is not a list, not even a strict list. I mean, not implemented as such. Maybe I've just implemented it as an array. Okay, so now, sure. So now cons, the actual cons of lists is super slow because you have to copy an array and etc. So you don't really want to do that. But cons D and nil D, they're completely free. I mean, it's just bumping a pointer somewhere. So it's kind of cool. You can still pattern match on that using GHC's wonderful pattern matching synonyms and view patterns and so on. Hope they're optimized away. I don't know. But yeah. You can, unsafe perform IO, that's pretty normal because I moved from something that was implemented terribly, terribly, with terrible types, scary IO types, and turned that into a safe API, a pure API. You can't really do that any other way. So it is the implementer's responsibility to give the right types. But you can't do that. That gives you completely different trade-offs. And when you're doing something that is unusual, or maybe distributed programming like me, making trade-offs is all there is. So, I think my point is, GAC does so much for us. It does garbage collection, it does fusion, all these things we don't have to think about. It's wonderful. Until you have to think about them. And then the fact that it's magically taken care of is absolutely no help. And at that moment, we really need to take that back into our own hands and make good, composable, safe abstractions for these things. Even the representation of your data is subject to this sort of manipulation. And linear types is a tool that, despite being very simple on the onset, gives you a lot of power to do just that. So, this was the end of it. You can find me on GitHub and Freenode. You can follow me on Twig.io's blog. As I mentioned, there's a paper. It's been recently accepted, so just you can watch the GitHub thing to see the final version soon if you were interested. There are going to be very soon proposals on GHC proposals, and you're all invited, if you were interested, to come, comment, give feedback, and just participate into the making of that into an actual GHC extension. Thank you very much. Go on.
What does SC82 mean?
Sorry?
You had a data type called SC82. What does it mean?
Someone else wants to add that question? So SC82 is an isotope of selenium. It has a very, very long half-life. So 100 quintillion years. So it was here to stand up for long-lived data.
So I think I'm a little bit confused. So you have the annotation of the single use of an argument on the function type. And so you have that essentially on the callee. But it seems to me naively that if I really wanted to do something about garbage collection, what I'd really want to have is that annotation that there's a single use of this variable. I'd want to have that transferred to the caller so that I can say, I can allocate a variable and I can say, I'm only going to use this once. Can I? Yeah. So my question is, can I do this using the machinery that you have introduced here? Can I build that myself? Sort of a dollar sign that sort of applies an argument and takes that out of scope.
I guess you can, yeah. But so if you want to do something that is like uniquely owned and has no alias and so on, you basically have to make an abstract data types that you will ensure by the API will stay unique. It is possible to set the system the other way, but there's a technical discussion that we can't have in 5 minutes. And yeah, ETSCO has a lot to say about that too. But my intuition, and it's hard to test really, unless we are starting making two completely different implementations and test them together, is that it's much simpler to just put the constraint on function, because it is a property of functions to be linear. But when you do that, you can still get the power by taking the consumer as an argument. And it is very expressive and fairly simple to implement. Whereas more uniqueness tailored schemes requires quite a bit more effort, I think. So my point in introducing it that way is saying this is the simplest way you can get all that. And I think it's a very powerful thing.
How does this approach compare to what clean does?
Okay, so that's the same question. So same answer. It's easier, but it's a sort of dual.
I'm just confused by some example you show where you have just malloc and free that take the PTR type, right? And you want to ensure that you will have to call free. But what if you have another method defined that accepts PTR? What if you had another function defined that could accept a PTR? Then you could call that other function, right? Yeah, but it has to, so because it doesn't free the function, so the way you will set up the API is functions that don't free the pointer will have to send to return a new pointer value, like do something in that slide, because they say, this is a proof that I haven't freed that pointer. So of course, in order for that to be safe, all functions that are primitive have to be implemented with care and correctly. That's what abstractions are all about, right? But yeah.
So what if I actually want to use the value twice? For example, I allocate the pointer, I want to write to something, then pass it somewhere or read from it. How do I do that with linear types?
I think that was the same question as well.
Was it?
So you just basically you're writing things in a sort of linear state passing style. So you take the pointer as a proof that it exists as an input, and you return the pointer again as a proof that it still exists and is initialized as the output. So for some types, you can also write duplicate things. So you have something that is linear, but you can sort of split it in two. So imagine you have a socket and it's linear, but you can plug two different things. There are two ways to do that: either anycast or multicast. You can have these two functions implemented. But if you're able to do that, then you do have to do some reference counting if you want to do early free, right? Because you can't free one of the two duplicates. So if you want to be able to do free without reference counting at all, you need to pass the state along and use it single-threadedly, or the state being a pointer in that case.
But then I need both to use a pointer and return it as an evidence that it exists. So this is not linear in itself, right?
The primitives will have to be that way. So if you have
But if I'm not writing if I'm writing like actual application code.
Yeah, well, you will be forced to return it because so the point is, so this was not about pointers where you can write, but you can also set up pointers that you can write. And the write function for a pointer would have type a pointer to a pointer of the same type probably, plus the value that so A to pointer A to pointer A. And it would consume the first pointer, it's not usable anymore. And the return value is just the proof that the pointer is still alive. So if a pointer value is a pair somewhat of a functor and the proof that you can read and write of it. And because your primitives are that way, you are forced to write your program that way as well. You're writing 2 writes in a go, well, you have this pointer that the second write returns. And you have to do something with it, and pretty much the only thing they can do is return it to the caller. Is that clear? Yeah? Okay.
One more question.
Okay. Coffee break. Yeah.
Are you able to implement all this just like on the surface of GHC then? You don't need to go down, you don't need to pass anything down in the extension to go further down into core or whatever?
Okay. This doesn't use any runtime modification, for instance. This is just abstractions that you put around FFI functions or something. So yes, in theory. In practice, I've got to modify core a little. And there are 2 reasons for that. One is, it's what core is for. Core is typed. There's this core lint thing that Simon mentioned earlier. And this is meant to ensure that every one of our optimization paths don't break invariants like types. And they're still allowed to be slower because you can't really check that yet. But they have to at least preserve type. And so we also basically want to be sure that they preserve linearity, otherwise they would be able to break things. Abstractions like that kind of rely on the fact that the underlying optimization won't suddenly make things duplicate things that it's not allowed to do. And it's very possible that there are a few passes that do that in some point. So it is still not completely resolved. The other reason is just purely an implementation detail, is that the types of the type checker and the types of core are the same. And because of that, modifying one implies modifying the other. And so I'm in the process of doing that at the moment.
Okay.
Yeah, and then checking linearity and so on.
So maybe we can move the discussion to the coffee break now, and let's give Arnaud another great applause.